Thank you so much. It's a pleasure to be here. It's such a huge event with so many people. I'm sitting down not out of some sort of disrespect. I am unexpectedly immobile, hopefully temporarily so. So you'll see me prancing about the stage the next couple of days. My first talk is about O-minimality and complex analysis. It's really a continuation of a subject begun by Peterzil and Starchenko, which has had some unexpected applications to number theory first, and then algebraic geometry, and now sort of a whole load of stuff. So with this first talk, I'm hoping to give a kind of down-to-earth introduction to the motivations of the subject and what it can offer in your mathematical endeavors. And then in the next two talks, we will get down to some applications. So this is really motivated out of this constant tension we all experience between algebra and analysis. So algebra is a very nice category in many ways to work with. It's very rigid, has a lot of automatic finiteness properties, but the problem with algebra is that it doesn't have enough of the functions that you might like, such as solutions to differential equations, sort of natural functions that show up in uniformization morphisms and things like that. And then holomorphic functions are sort of a big enough world to encompass most of what shows up. And a good case to think of for this is Hodge theory throughout the talk, which is where we're sort of aiming. But it has all sorts of messy properties that you might run up against if you're not careful, such as essential singularities. Things might even be worse. You might have complicated domains of analyticity, and so on and so on. And the idea behind O-minimal complex analysis is somehow to get the best of both worlds, to get a category which is rich enough to have most of the functions that you might want to deal with. Of course, it won't have all of them, but it'll have a lot, but still sort of tame in some precise ways that hopefully we'll make clear. And one heuristic way to think about this, though it's a much more broadly applicable notion, is you can think of O-minimality as sort of a substitute for compactness. So in many cases, if you're dealing with algebraic varieties, the proper case, the compact case, has nicer properties. And if you're non-proper case, O-minimality might be something to reach for. So let's list some algebraic properties that we might want to emulate with our new category that we're making. So one of the nicest properties is Chevallier's theorem, that it has a precise formulation in terms of constructible sets. But one of the sort of easiest intuitive ways to think about it, I think, is no matter what you do with algebra and first order logic, you don't get sets that are that bad. You only get constructible sets. They're very simple. So concretely, if you get a discrete set, it's going to be finite. And more generally, the topology of any algebraic set is going to be simple. If you take the closure of any constructible set, you get something algebraic, something constructible once again. And you have this nice auto-uniformity property, which shows up a lot in applications to number theory in particular, that if you have an algebraic parameterization of something finite, it's uniformly finite. So dimension sort of can only get so high, cohomology can only get so high, that kind of stuff. Okay. So with that, let me give sort of a non-logician's introduction to O-minimality. This is introduced in different ways depending who the audience is and who the presenter is. So I'm most comfortable with collections of sets. And essentially, you can think of an O-minimal structure as just a collection of allowable sets. Now, what world of sets are we allowing ourselves to talk about? So it has these properties that you, well, first of all, it's given by in every dimension. For every n, you look at R to the n. So it's a real theory fundamentally, even though we're going to apply it to the complex numbers later on. And you have this subset S to the n, Sn, boom, here we go, which has a bunch of properties. So it should be closed under intersection union complement. It's Boolean algebra for every n. It's closed under permutation of coordinates. So none of the coordinates are preferred, are distinguished. If you multiply a set, take the Cartesian product of a set that's allowed, the set that's allowed, you get another set that's allowed. So Sn cross Sm is in Sn plus m. And you have this axiom here, which you can think of as quantifiers are allowed. So this is sort of that there exists quantifier. If you take any set in Rn plus 1 and you project it to Rn by dropping the last coordinate, you get something which is also allowed in Rn. And finally, this is not typically imposed on O-minimality outside of applications to algebra. You don't have to have addition and multiplication. You can just talk about orderings or other structures, but we're going to throw it in because that's all that we're ever going to think about. I want S3 in 3 dimensions. I want to have the graph of addition and multiplication, which essentially means that we have all polynomials, all real algebraic sets are in our collection. So far I've just defined a structure for you. There's nothing O-minimal about this. The O-minimality comes from the following sort of special axiom, which is that in 1 dimension, the allowable sets are precisely finite unions of points and intervals. And the intervals can be bounded or unbounded. So you can have either infinity inside of your intervals. So these are actually mandated by the previous axioms. As soon as you have algebra, you have inequalities because squares are positive and you can reference that. And so you can define intervals, you have finite unions and such. And O-minimality says there's nothing else you can define in dimension 1. So some people here have seen this a lot and are very familiar. For those that aren't, when you first see this, it's kind of surprising, perhaps, it was to me, because all the interesting stuff, sort of the juice is happening up in higher dimensions, and all you're doing is requiring a restriction on what's happening in dimension 1. But the point, somehow, the magic comes from the fact that if weird things were happening in higher dimension, you could intersect and project, do interesting things like that to get weird stuff happening also in dimension 1. So this proves to be a very strong restriction. And some conventions, sorry, just for talking about the theory, is that if you have a set in one of these SNs in your structure, we say that set is definable in the structure. Functions are definable if the graphs are definable, that's standard. And even though this is a real theory, we're going to want to apply to the complex numbers, which we do in sort of the usual way. We identify C with R squared in any reasonable sense. So most common one is take the real and imaginary parts. And then once you have that, you can talk about definable sets in C to the n with respect to any O-minimal structure. Okay, so even just assuming O-minimality formally, not knowing anything about your structure, you can prove a surprising amount based on the assumption of O-minimality. In fact, it's much harder to prove some structure is O-minimal, that O-minimal structures even exist, than it is assuming O-minimality to deduce a lot of interesting consequences. So I'm going to list a few consequences for you. So you have finitely many components, connected components, if you're definable in an O-minimal structure. And those components, those connected components are all in fact path connected, so you don't get any super weird topology. And you have uniformity in families, like we taught. Have a definable family that's finite, and it's uniformly finite. You have good cell decompositions. So I'm sort of jumping the gun. There's many previous theorems here. But for any k to any order of smoothness, you have a finite c to the k cell decomposition, either triangulation or by usual cells, however you prefer. I should mention that it's not true. It's known not to be true if you replace the ck by c infinity. There are some O-minimal structures in definable sets that don't admit that. But this is a lot for applications already. So in particular, you have a good dimension theory in the usual way for definable sets. If you have a definable set, then the closure is definable, just like we wanted. And you have definable choice, which is if you have a surjection, a definable category, you always have a definable section. Of course, that section might not be continuous, but it will be definable. And the proofs, like I said, are sort of elementary. So just as an example, I'm going to give you the proof of one of these, chosen at semi-random. So like I said, if A is definable, so was its closure. And how do you see it? Well, you can define the closure without any limits, just with sort of epsilons and deltas in this usual way. I'm not going to read it out, but I'll leave you to check it. And this here is a definition, right? Because every existential quantifier is a projection, and every universal quantifier is a projection with some complements thrown in. So this just defines for you a bar out of A. And the other proofs are sort of similar, but you know, there's more work to be. They're likewise elementary. Okay, so now you can ask, are there any examples of O-minimal categories? It's sort of great to, in principle, have these applications, but do these things even exist? So they do. And a couple of them were discovered before the notion of O-minimality was formalized. And O-minimality actually grew out of an attempt to sort of codify these great properties and try to see if there's other settings in which we can do the same thing. So the first one is due to theorem of Tarski and Seidenberg. I can't find a precise date for this theorem, but everyone says the 50s. So it's our alge is basically the smallest O-minimal structure as we have defined it. Just take the axioms as given, take addition and multiplication, and do all the things that you're allowed to do. And so you get the structure of semi-algebraic sets. So everything you can do with real algebra. You can think of it as you have plus and times. You also have the inequality, as I mentioned before, because squares are positive. So just armed with those operations, what can you define? That turns out to be an O-minimal structure. This one is quite a bit trickier. So this is proven by Wilkie 96. So this is Rx. You can think of X as either a basic operation, sort of given to you in your structure. You can just throw in the graph of the real exponential. It's very important that it's the real exponential and not the complex exponential, as we'll talk about in a second. This is proven by Wilkie in 96. And all of these theorems about proving that some structure is O-minimal, as far as I know, all the proofs involve some version of elimination of quantifiers. So this one here is straight elimination of quantifiers. Rx is not, but you prove that every definable set has some special form that you can control. Okay, Rn actually came before, but it's more complicated to define, so I listed it after here in my list. And there's a few ways to define it. The most intuitive I find is you throw in R-alg, so you have plus and times, you have algebra, and you throw in all over-convergent, I said holomorphic, but it's better to say analytic functions. So essentially, you can't throw in all analytic functions, because if you throw things in that just converge at the boundary of the unit ball, you're going to get all sorts of messy behavior, and that's not going to be good. Instead, what you do is you take functions that converge on the unit ball, and you throw in their graph on any slightly smaller ball. So this is where the over comes from in overconvergent. And you look at what that generates, and that gives you this O-minimal structure, R-alg. So these two actually don't contain each other. It's sort of intuitively clear. I don't know if it's formally clear, but I'm sure everyone believes that R-alg is in some, Rn is in some precise sense much larger than Rx, because you have all sort of power series thrown in. If you're in the wild, you probably have some analytic functions. You're automatically in Rn. That's sort of a useful category. But it turns out that Rn doesn't contain the real exponential. It's what's called polynomially bounded, meaning if you take any definable graph in one variable in Rn, and you look at how it grows at infinity, it's going to grow no faster than some power of x. So polynomially bounded comes in. And there's a beautiful theorem that as soon as you're in an O-minimal structure that's not polynomially bounded, you automatically contain Rx. Rx is the smallest non-polynomially bounded structure, which is kind of cool. So these two are really different to each other. And then Van de Dries and Miller in 94 prove that even if you smush them together, you allow one of the other. This isn't just a union, right? You have to union the structures up sort of naively and then take everything which is generated by those functions. Now you can plug in real exponentials into power series and so on and so forth. That's still O-minimal, and that's not free. So we know there's no largest O-minimal structure. In general, you can take two O-minimal structures, put them together, and they will generate a non-O-minimal structure for you. Nonetheless, even though there's no largest one, Rnx so far seems to be the main structure that's useful for algebraic geometers and number theorists. So I have never written the paper that's not using Rnx, though I hope to one day, as I will describe a little bit later on. So one that I think is worth pointing out, which I think is useful for some other applications, and it's easy to understand, is if you take any O-minimal structure, in particular Rnx, and you take its Pfaffian enclosure, that's also O-minimal. It's a theorem of Speiziger. And in fact, if you take Rn and throw in its Pfaffian enclosure, then you will get the exponential, because log is just integral of 1 over x, and once you have log, you have the exponential just by a flippy. So what's the Pfaffian enclosure? It basically means you're allowed to integrate certain types of functions. It's a little bit more general than that, but you think of it that way. You can throw in indefinite integrals into your structure. Okay, so henceforth, if I just say definable, I mean definable in Rnx. Most of the stuff works in more general O-minimal structures, but there's no real need to think about those if this is what you're most comfortable with. Okay, so some example of the most common types of non-definable functions, which we still want to work with, are periodic functions. So we'll build up here a little bit, but the simplest function you might want to be definable that's not definable is sine of x. Why is it not definable? Where it's periodic. So in particular, if you take a level set, for example, sine inverse of 0, you get an infinite discrete set, and we ruled that out with our O-minimality axiom. So sine is not definable in any O-minimal structure. This is why we had to restrict the real exponential earlier, because the complex exponential sort of has cosine and sine built into it. Okay, so what you do in this context, what's been proven very fruitful, is you take a periodic function and you restrict it to a fundamental domain. You just sort of cut off its graph on a fundamental domain, and that's going to be definable. And then armed with that, sort of, you can still bring in the O-minimal machinery, and you also have the fundamental group that acts on you due to your periodicity, and that sort of allows you to think about the whole function in an O-minimal framework. So in particular, sine is analytic, and it's overconvergent on any bounded interval. Although, of course, it's not overconvergent on the entire real line. So sine is allowed, its graph is allowed on any bounded interval. So likewise, the complex exponential is not definable on all of C, but is definable on a fundamental domain on the vertical strip. I'm always going to throw in this 2 pi I z here, being a number theorist. And one way to see it's definable is, you really need Rnx. This shows up a lot in Hodge theory and a lot of number theoretic applications, is that you have the e or the y right here, and you have the cosine and sines here. So both Rx and Rn are playing a role. One thing which is not going to show up in my series of talks, but is very exciting recently, is you, of course, don't need all of Rn to talk about the functions cosine and sine. They're not arbitrary overconvergent functions. They're very special. They satisfy some sort of differential equation, for example. And you can try to look at smaller O-minimal structures. So maybe the smallest one generated by sine or generated by all solutions to differential equations of a certain kind. And there's a theory right now of sharp O-minimal structure pioneered by sort of Bignamini and his coworkers, who, for number theoretic applications and for certain more refined questions, really do require this sort of this restriction, and they prove a lot more for these smaller structures. Okay, to get us closer to where we're eventually going to be, if you look at the J function, which is a periodic function on the upper half plane with a more complicated fundamental group, SO2Z. Once again, it's not definable, but it is definable on what I'm going to call the usual fundamental domain. I'll put a picture up in a future talk, but not this one. Hopefully people know what I'm talking about. And how do you know this? Well, the fundamental domain is the sort of rectangle we've seen before, maybe a little bit smaller than that. And so you can take J of Z and you can write it as a Laurent series in Q, e to the 2 pi I Z. So it's Q inverse, which is okay because Q is okay, plus some power series in Q, which converges all the way up to 1. The fundamental domain sits above the x-axis. So all we need is some ball with radius strictly less than 1. And so it's an overconvergent series. So this is why the J function is definable in Rnx. You can do the same thing with holomorphic modular forms. You got to make them function somehow, but okay, that's not particularly hard. All that's definable. And with slightly more work, but in the exact same vein, you can do the same thing for arbitrary Shimura varieties and the usual fundamental domains. All the automorphic forms we normally deal with are definable. The one thing I looked up when writing this talk is whether the non-holomorphic forms are definable. And to my great annoyance, I couldn't answer this one way or the other. Because in particular, even on for classical mass forms, if you look at their expansions, you get Bessel functions. And so I asked, is Bessel functions definable in O-minimal structure? And it seems like nobody knows. If they were oscillatory, the answer would be no, because that's not allowed in an O-minimal structure. But they're not. They're eventually monotonic, and all the derivatives are also eventually monotonic. So maybe it's simple, but I couldn't figure this out one way or the other. So I'd be curious if somebody knew the answer to whether mass forms are definable. Okay, so now let's take the theory of O-minimality and bring it together with complex analysis, which is the framework we eventually want to be working in. So this, as I mentioned before, was really pioneered by Peterzil and Starchenko, who had a series of papers on tame complex analysis, who were working sort of more generally than I'm working here. They're working over totally ordered fields and their complex extensions and stuff like that. But we'll work in this more, we'll restrict ourselves to this more classical framework. And they made this almost sort of very surprising, naive definition that we're going to talk about sets being definable analytic if separately they're analytic, meaning holomorphic, and definable in your own minimal structure. So there's no subtle way to smoosh them together, you just kind of do it. And it turns out that this behaves in very nice ways. So one of the main reasons this is a nice category to work in is that since your functions are all definable, you can't have central singularities. And here's a very simple proof of this. There's proofs relying on smaller hammers, but this is a very quick one. So if you have a function on the punctured disk, it's got to be meromorphic. Why is that? Well, by definability, the inverse image of anything is finite, but Picard tells you that if you had an inverse singularity, then all of these level sets, and maybe an exception, should be infinite. Therefore, you're meromorphic. So that's a very simple observation. And one easy corollary, which sort of hints at what's to come, is if you look at definable holomorphic functions on all of C, you of course have polynomials, because we've allowed ourselves algebra. But this says there's nothing else, because at infinity, you also have to be definable, therefore you're meromorphic, and so only polynomials are allowed. Okay, so where we're building up the theorem that's really most useful for applications is, in what I'm going to talk about, is Chow's theorem, which I'm going to remind you of here. So take a closed analytic subvariety V in projective space, so it's important to be closed, then it has to be algebraic. The solution, some algebraic variety, it's cut out by homogeneous polynomials. And sort of justifying a little bit the heuristic, which is also I stole from Peterzil and Starchenko, that O-minimality is a substitute for compactness. If you're instead in affine space instead of in projective space, so you don't have compactness to help you out. If you insist you're closed and definable, then you also have to be algebraic. Nothing else can happen. So before moving on, these are both, they were stated this way, but they're both easily generalized. You can replace Pn by any proper algebraic variety, so compact over C, using Chow's lemma, actually. And likewise, Peterzil and Starchenko, they didn't write this, but it follows immediately that if you work with any algebraic variety W, the same theorem holds, like a closed definable analytic subvariety of W, then it has to be algebraic. Okay, so one nice corollary of this, I find, this isn't maybe, oh, yes, thank you. I debated defining this and decided not to, but yeah, sure. So one way to say is you can cover by affine to definable in each one. You can define, you can define definable manifolds without much trouble. We'll do it a little bit more detailed later, but just finite covering. The only real, as I pointed out again, the only real difference in the definable world to the usual world as far as manifolds are concerned is you're only allowed finite addresses because you're doing logic, sort of, so infinite things aren't good. Other questions? Yes. Yes, so we're building towards a Gaga theorem as sort of the main thrust of the talk. So great question. We'll get to that in a second. Yeah, so one nice consequence of this is that in the definable analytic world, contrary to the analytic world, you have a canonical algebraic structure if you have an algebraic structure at all, right? In the simple way, if you had two, you could take the product, that would have to be algebraic by this theorem, so it'd be the same. Just like for a compact analytic variety, that has at most one algebraic structure if it has one at all. So that's false for non-compact algebraic varieties if you're not in the definable world. An easy example is if you look at C squared, you have the algebraic structure given by Z and W are coordinates, but you can also look at Z and W plus e to the Z as coordinates. So another way of saying this is you have analytic automorphisms that are not algebraic, you have a lot of them. But as a corollary of this, instead of asking the question, does there exist an algebraic structure on some analytic variety, which is what sort of is typically asked, if you're in the definable analytic world, you can just say, is this algebraic or not? And that sort of adds an additional clarity that makes this category a little bit easier to work with. And another thing to observe is that even though we're in the definable world, it might seem like a huge restriction because analytic functions are much more general. In fact, regular Gaga is implied by this O-minimal version just by using the structure Rn of overconvergent functions. Why is this true? Well, essentially, any compact complex manifold can be defined in Rn because you can take open coverings and you can use functions on those open balls to define it. But then you can shrink your coverings a little bit in the usual way, and your functions become overconvergent. So anything you can do for compact complex varieties also exists in this definable world. Okay, so our goal is to get a Gaga analog. That's what's going to be most useful for us as far as applications to Hodge theory and Shapur varieties later on. And one thing that the motivation for this really was to do some kind of deformation theory. If you want to do any kind of deformation theory, you need to work with non-reduced spaces, and then it sort of becomes hard to work with sets. You have to work with some kind of sheaf theory. You need some stronger categories. What we need is what one thing in particular that becomes very important is some Chow theorem, but for non-reduced spaces. So you want to know that if you have, so what you do know is that if you have a proper algebraic variety and you take some closed analytic subspace, so possibly non-reduced, then it's algebraic. So there exists some algebraic subscheme whose analytification is your guy. So you can think of like a closed analytic subvariety subset together with like a tangent field on it, for example, or a more complicated infinitesimal structure. We want a way to say that in definable world. Now there is actually, I should point out that the model theorists are very good at this. So one benefit of working, this is a bit of an aside, but one benefit of working with arbitrary sort of real ordered field in more generality is a lot of these auto uniformity claims actually follow in that way. So what you can often do is instead of working over R, you can work with like Laurent series or power series over R, because the field of Laurent series is also a naturally real ordered field. And then if you prove all these theorems, these decompositions and these finiteness theorems over that field, that specializes to uniformity theorems over R. So in principle, all the infinitesimal stuff can probably be done in some way by working over some field like that, some extension of R by some power series variables or something of that form. We don't do that because I don't know how to at least, but it's an interesting perspective to keep in mind. So, okay, what we're looking for is something like this, and that, as was mentioned, is usually a corollary, or the easiest way to deduce it is the corollary of Serre's Gaga theorems. So they're a little more general than this, but I'll just isolate this piece of it. If you have coherent sheaves at your disposal, it says that if you're in an algebraic variety or scheme, then the category of algebraic coherent sheaves and the category of analytic coherent sheaves are naturally equivalent. And the functor here is easy. If you have an algebraic coherent sheaf, well, algebraic functions are also holomorphic, so it gives you a coherent sheaf, and they're the same. And the reason it implies Chow theorems is because given a subscheme or a subspace, you can look at the ideal sheaf of things vanishing on it, for example. So that's how this becomes strictly more general than the statement about sets and subsets. Whoops. Okay. So it's not just this diagram then joined with Baker and Brunnebar, it's the following results as well. But this diagram did take me an hour of playing in LaTeX, and this is as good as I could get it. So if anyone knows how to make this, I rotated it, which I'm very, very proud of. But if anyone knows how to move this down here, please see me after the talk. Okay, but the idea is just like we have this analytification functor from world of algebra to the world of analysis, we propose this definabilization functor to definable analytic spaces through which this functor sort of factors. So you can always get the definable analytic space and then forget the O-minimal structure and just get the analytic space that's available to you at your disposal. And so it allows you sometimes to steal theorems for this arrow into theorems for this arrow. But this arrow has some nicer properties, as we'll see, than this one. I don't know anything interesting to say about this arrow.
Which arrow are you pointing?
Sorry. Over here. The analytification arrow sometimes allows you to steal results with the definabilization arrow because you can just restrict back to your analytic structure, is all I'm saying. Sorry, to me it's very clear, but I have no idea because I'm also a side. I guess there. Thank you for pointing that out. Okay, and the notation I'm going to introduce is this DEF for definable. So given a variety, if you analytify it, you write AN, same for sheaves or whatever associated structures, and you have this def as analog. Okay, so how do you make definable analytic sets? Let me give you a quick introduction to the category. And like I mentioned to Daniel a minute ago, the main difference here is that coverings are finite. When defining sheaves or gluings, everything has to be finite because secretly we're constantly borrowing from algebra, which only allows finite unions and intersections. Everything sort of breaks down. One way to think about it is any holomorphic function is locally overconvergent, right? But you can't expect it to have the properties of overconvergent functions. So locally in this world always means you have some finite cover where things are true. Okay, so the basic objects for your site are definable open sets and with finite coverings. That's the site we're going to be working on any space. And this site makes sense without analysis. This makes sense on definable manifolds sort of more generally. And the basic structure on C to the N is you make a locally ringed space with the definable sheaf, which just takes definable open set U and returns all definable holomorphic functions on U. This is clearly a sheaf on the definable site. And the main theorem we prove, which allows us to sort of build the theory sort of in parallel. Earlier work in the analytic world is this version of Oka coherence, which is that for this site, OC to the N is actually coherent, which allows you to sort of pass from local global generation to like global generation, things like that. Isn't there a def? There's a def here. Oh, there's no def here. Sorry. OC is also coherent. That's regular, okay. But yeah, sorry, there's a missing def. Okay, and the basic objects, the analogs of sort of affine varieties. Oh, before that, I should mention that this theorem, it was due to us, but there was earlier work by Peterzil and Starchenko proving a version of Oka coherence. It was a global version. They talked about ideal sheaves on sort of an entire open set at once. They didn't really talk about these finite coverings, but a lot of their ideas go into our proof. Okay, so the basic objects, the analogs of affine varieties, are very similar. So you start with a definable open set. You look at a finely generated ideal made up of global on this definable open set, definable holomorphic functions. And your space becomes cut out by this ideal with the induced definable site. And you just take the quotient sheaf like you would normally do with respect to the site. And that gives you the sort of basic definable analytic set, we call them. And then if you want to build a general definable analytic space, you just glue these using some sort of finite atlas. And that's all you do. And then Oka coherence allows you to prove this is a nice category. So in particular, one of the, or some of the structure theorems that we prove is you have a Nullstellensatz in sort of the strongest sense, which allows you to talk about reduction, which is actually not a priori obvious. If you define basic definable analytic sets this way, it's not a priori clear you can take the radical of I and also get something that's sort of reasonable, but this tells you it is. And push forward in general is complicated. So at the end, I'll talk about some things that are still very much missing in this world, but we do have a push forward of coherent sheaves under finite maps. Okay. That's right? Yes. For finite maps, just finite. Yeah, just fine. We do not have it for proper maps. Yeah. But we're close, maybe. We don't have it. And since polynomials are definable, again, it's easy to define a definabilization functor. If you have some Minkowski polynomials, you just consider them as definable holomorphic functions. And you can also definabilize coherent sheaves the same way. Everything sort of goes through. Okay, so to go back to Gaga, here is the version that is true. So first of all, we do just get the straight up non-reduced chow, which is kind of the thing we're most after in some sense. So we can now talk about definable analytic spaces that are not reduced. And if you've got a subspace of a global algebraic guy, then you must be algebraic. The exact same theorem holds. Gaga mostly holds, which is enough for most applications with a caveat. So you still have this map of coherent sheaves. That's not hard. And we show it's exact and fully faithful, which is important for us. But we it's not surjective. So we show the essential image is sort of its own big piece that's closed under sub-objects and quotient objects. But you do have definable analytic coherent sheaves that are not algebra in this world. And yeah. No, typo. Yeah, I mean, true, but yeah, we don't need it now. The whole point is not to need it. Yes. Sorry, the question was, this says let W be proper. Of course, the whole point of this definable stuff is to get rid of the proper assumption. So you should just scratch out this proper here, and the theorem still holds as stated. Yeah, both these propers should be gone. This is a Oh, this should be a not an equivalence of categories. Yeah, that's right. A good lecture makes the audience think and engage with the material. Apologies. So remove the proper, and it's not an equivalence of categories, but not in general, at least. Any other mistakes in the slides? Okay.
So you really have the lack of projectivity, the things that are the additional stuff is still quite mysterious.
In general, it's mysterious, but here's a very explicit example of a kind of thing that's not algebraic. But the answer is yes. So we don't have anything like an understanding of how much is missing. There could be a lot of stuff, but here's a very simple example. So this typo I noticed, sorry, the G for some reason compiled on my computer, but none of the slides. So this should be GM. We're going to work on just GM, so the puncture plane. And for any alpha, I guess it could be in C star, consider the local system with monodromy e to the 2 pi I alpha. So you go around and you multiply by e to the 2 pi I alpha. And local systems that haven't defined the definable world, but they're the same thing. Things that are locally trivial. And you can just trivialize with sectors. So it's easier to define this local system. And we're in a category where we can just take this local system, we can tensor it with a definable structure sheaf, and we can get a definable line bundle. And it turns out that, so for some O-minimal structures, this is like not definable for most alpha. But even for R and X or any O-minimal structure, it turns out that if alpha is not real, then V alpha is not trivial as a line bundle, as a definable line bundle, and therefore it can't be algebraic. Algebraically, there are no interesting line bundles on GM. And the idea behind it, I'll give a proof, but the idea is that the natural section of this is Q to the alpha, right? That's the natural sort of multi-section, which will trivialize the monodromy, and which will give you a real exponential if alpha is real, and if alpha is not real, it gives you an oscillatory non-real exponential. So that's the idea behind why this isn't definable. It's kind of cute, so let me actually prove it's not trivial, because it's not enough to say this isn't a trivializing section. You have to show that there is no trivializing section. So the proof is it's kind of cute. So it's the following: assume that it were trivial, then you would have some trivializing section f of q. So it would look like q to the alpha times e to the gq, where g is holomorphic and single valued, up to at least adding an integer that's true. And then what you can do is you can take log derivatives and you get some definable single valued function like this, which means that g prime is definable. And so g has to just be a polynomial. There's nothing else for it to be, a Laurent polynomial. And you can probably finish in many ways here, but a cute way to finish is to say, let's look at the values where f is real. That should be definable, but it's the same as those q's where the imaginary part of this polynomial, which is a polynomial in itself, plus the imaginary part of alpha times log q is in Z, another typo, and that's infinite discrete. So that's not going to be definable. Okay, so you even have definable. So again, importantly, I want to stress, this is not going to be, you can define this local system in any O-minimal structure, and it's not going to be trivialized in any O-minimal structures. For a while, we thought maybe if you pick the right O-minimal structure, you'll get some nice equivalence, but it turns out no, that you never do. Okay, so what's lacking from the theory of definable analytic spaces? The main thing that's lacking for us is a good cohomology theory. So concretely, even Stein factorizations are something that we can't quite do in general, though we're close on this point. We can do definable Stein factorizations if you have a a projective morphism of definable analytic spaces, or if you're dealing with semi-normal spaces, which is, pretty good, but we can't do it in general. And it is in fact important in general, again, because you want to do deformation theory arguments and stuff, so you can't really restrict to semi-normality. This would follow from, but we don't have a good definable coherent cohomology. So I should say sort of two things about this. First of all, there is a lot of work for example, by Edmundo and collaborators. He has a series of papers on this. There's also more recent work on their own cohomology. So I don't mean there's no definable cohomology theory. Specifically, I'm talking about the analog of coherent cohomology in this definable analytic category. And if you make the obvious definition of just take sort of usual check cohomology with coherent sheaves, you get things that seem to us to be too big. You get like uncountable dimension spaces, even in very, very basic worlds. So this is something that we don't know the definition of, and I think would be very interesting to get. And a natural question that shows up, which I think we still don't know the answer. I haven't checked this with Ben or Johan, but I believe I certainly know the answer to this question. Is that a fundamental sort of thing is a Del-Bar-Poincare lemma. So you can phrase this in any O-minimal structure because you can differentiate. And the question is, do you have it in some O-minimal structure? And early on, I mentioned that there might be, I was hoping that there's other O-minimal structures that'll start making their appearance in algebraic geometry. And so my hope would be that in some Pfaffian closure or iterated Pfaffian closure of Rn(x), maybe you have a Del-Bar-Poincare lemma, but I don't know one way or the other. I should mention, like, the reason that the obvious proof fails is there's a limit in the obvious proof, right? You like do some overconversion thing in a smaller disk, you can do that. Then eventually you take a limit, and you can't take limits of sort of, there's analysis that shows off with bounds, and you can't do that in this world. Okay, so one advertisement for the next talk or the next series of talks, we've developed this machinery, but all the sort of Gaga and Chow's lemma stuff is in the direction of all these definable analytic spaces that show up in algebra are just algebraic anyway. So what's the point? Well, there's at least one very interesting example, which is period spaces, which, as I'll talk about next time, have a definable analytic space structure that's very natural. And they also have lots of algebraic subvarieties given by period morphism from moduli spaces of algebraic varieties, but they're known not to have any algebraic structure. So this is a nice case to put this theory to work. That's the motivation for developing the theory. So yeah, these admit period maps from moduli spaces that contain algebraic subvarieties, but they're not themselves algebraic. And so as a corollary of all this technology, if you have definable analytic results on D mod gamma and you pull them back somewhere algebraic, you get algebraic information. And that's sort of the philosophy is you can, like if you're in the Yoshimura world, like AG for abelian varieties, you have a universal family. You can sort of prove results and then they're true for all abelian varieties and all families of them at once. You don't have universal families in general, but this is meant to try to act as some kind of substitute for that fact. That's it. Thank you so much.
Okay, thank you very much for this great talk. Are there questions? If you have a question, raise your hand and wait for the microphone to come to you.
Okay, so my question is, do you know if there is any relation between this kind of O-minimal complex analysis and this kind of attenuated models that Clausen and Schulze use for their approach to?
I don't know of any precise relation between them. No, you mean this this p-adic stuff or this recent like condensed stuff that they're doing? The condensed stuff. They do, yeah. I don't know if, so the question is about the condensed mathematics because they also use overconvergent sort of function in their stuff. I don't know of any precise relation. I mean, in some philosophical sense, in general, they're trying to do the same thing, but no. There was a no.
Hello, thank you for the very interesting talk. You mentioned that the coherent cohomology theory is a little bit poorly behaved in the naive sense because the groups can be enormous or something. Sort of on the other side, do we have some of the standard sort of coherent cohomological vanishing theorems like Sayre or Kodaira or Kalmar-Buick? No, okay.
No, so one of the problems is that the groups are, I think, never zero for any of, like they're always, as soon as you're positive dimensional, even for C, the groups end up being enormous. Yeah, we don't have anything like that.
So if I understood your GM example correctly, you
Yeah.
made some definable line bundles whose analytifications were trivial, but which were not.
Yes.
So is there a definable Picard group? Picard space?
Picard group for sure.
No.
Is there a definable Picard space? No, I don't think so. I think for the same reason. I think you probably show that it's like has way too big dimension, but I also don't know of one. Yeah. Mhm.
Thank you for the talk. Can we use O-minimality to give new proofs of the classical Chow theorems or the classical sort of Gauge results?
Well, so it did, right? My backspace button is working very slowly, but oh, there, I think I had it here. Yeah, nope. Okay, well, whatever. Definable, it's up what I mentioned. The definable chow does imply regular chow because if you're compact, you're automatically definable in Rn. You could be defined using overconvergent functions. So the answer is yes, and it's been done. Although I guess I see. I guess for the Gaga, it's a good question. You could ask if it gives a new proof also of that final piece, the surjectivity for the Gaga. I haven't thought about that. Yeah, it's interesting.
So is it possible to classify all different definable structures from the Pure space in general?
Oh, to classify them?
Yeah.
No, there's way too many. In general, a definable analytic space, sorry, an analytic space admits a huge amount of definable structures on it. So you can show, even like a good example is, look at C star. Peterzil and Starchenko talk about this example. So the usual definable structure is lift up to C, take the fundamental domain, which is the usual rectangle, just copy the definable structure from C and you're good. But you don't have to do that. You can take your rectangle and you can slant it. And that's just as good of a thing. And you can put a definable structure there. And it's wildly different. And it's kind of cool. They show that for a torus, like even for any abelian group, Lie group, the usual definable structure is the correct one. It's sort of best behaved in some ways. But the short answer is there's tons of them.
How well is equivariant geometry preserved by this definable Gaga functor?
What do you mean concretely? Sorry.
So if you have some kind of group scheme acting, and you want to explore the equivariant, I know you said there's no cohomology, but even just sections of vector bundles with the G action, how well is that preserved when you pass the definable spaces?
Yeah, that's all. That can all be talked about in the definable category. I think very well is the answer. Yeah.
Any more questions? Okay, well, thank you very much, Jack.